Hello, everyone. Worked several moments of inertia problems with integrals. Now I'm going to work a couple integral problems where I'm going to use the integral to calculate the center of mass. In this first one, it's a triangular plate whose width is h, or excuse me, width is w and height is h. So it's a generic problem that works for any triangle, basically. And I'm going to calculate the x center of mass and the y center of mass. Let me turn on my document cam and show you what I'm talking about. So you can see the plate here. It's basically, actually, let me get a little better focus. I'm not impressed with that. There you go. You can see basically it's a triangle. It's a right triangle. It's got a width W and a height H. And I want to calculate where the center of mass would be. I think you all can tell it should be closer to this side than this edge. So it should be down here somewhere. And it should, of course, be closer to this side than this side. So it should be somewhere around in here. But the formula that we use are xcm is equal to the integral of x dm over the integral of dm. And the ycm is the same thing, except replacing the x's with the y's, y dm over the integral of dm. Now I'm going to use a different mass element and differential mass element in each one, so I can't just work the dm once and for all. But in the first case, I want to take the xcm. Okay, so the xcm, just like all integrals, the integrand you don't want to change very much over the entire dm. So it really would be smart of us to make sure that our differential mass element is very thin in x. So what I'm going to do is imagine a little mass element right here whose width is dx. Now I could make this an equation for this line right here. Notice it goes through the origin, so it should be y equals, the slope is h over w, so h over w times x. So then I can say, well, the volume, or excuse me, the height of this rectangle, its width is dx, but its height is h over w times x for any given x minus 0. But obviously you don't have to put that minus 0 in. So I'm going to say dx, or excuse me, I'm going to say dm is equal to the area density sigma. So I'm pretending this plate is a what we call in calculus a homogeneous lamina. So it's a two-dimensional surface that's uniformly made. So it's basically this sigma is a constant. That's what uniform means. And it'll be that times dA. Of course, now I got to compute dA, and that is dA is going to be the height, which is h over w times x, technically minus 0, but again, I don't have to show that, and then times the width, which is dx. So now I can calculate the integral of x dm is going to equal the integral of x times sigma h over w times x times dx. I'm going to pull out all those constants in front. So I got a sigma h over w in front, and I got integral x squared dx, and I'm going to integrate that from x equals 0 to w. Of course, that's pretty easy. The integral of x squared is just 1/3, so I'm going to say sigma h over w over 3w times the integral, like I said, is 1/3 x cubed, and when I evaluate at w, I get w cubed. When I evaluate at 0, I get 0. So it's going to be w cubed here, the 1/3 being in the bottom. Obviously, this exponent of 3 can cancel out with this w right here and leave a 2 up there. In principle, I can go ahead and say that sigma is equal to the mass of the triangular plate divided by 1/2 base times width, which basically is 2m over hw. I could put that in there, but really I don't need to do that. I'm just going to leave it as is. I'm going to say the integral happens to be sigma h over 3 times w squared. And now I just evaluate the integral of dm. And when that comes out, these things out in front will cancel out, including the sigma. So you can do it that way, but like I said, I'm going to do it this way for this particular time. So it's just the integral of dm, which is the integral of sigma times h over w times x times dx. So I'm going to pull out all the constants in front and say sigma h over w times the integral of x dx, and I'm going to integrate from x equals 0 to w again. Obviously, this is going to become 1/2 x squared, and when I evaluate that at w, it's 1/2 w squared, and it's 0 there. So I'm just going to write sigma h over 2w times w squared. Again, this will leave a 1 there, and that'll cancel that out. So the x center of mass will be sigma h over 3w squared over sigma h over 2 times w. You can see clearly the sigmas cancel out. I'm going to get a 2/3. Also, the h's cancel out, and then one of the w's cancel out. So I ultimately get 2/3 w is the x center of mass. So, and that's a general rule with the triangles. You do go to the biggest, thickest side, if you will. So the thickest side is this side as opposed to that one. We're talking about x. So I go 2/3 of the way there, and that should do it. That would also suggest this one should have a y center of mass of 1/3 h. So let's work that out now. Now, when we're dealing with the y center of mass, again, we don't want the integrand, which the y center of mass, remember, is integral of y dm over the integral of dm. We don't want the integrand to change significantly over the infinitesimal area. So I'm going to use green this time, and I'm going to use this as my differential mass element. So this is dm, and of course, y center of mass is equal to integral y dm over integral dm. I'm going to say my center of mass, or excuse me, my differential mass element. I'll keep it in green so we remember which one it came from. So dm is equal to sigma dA. But now I want to take the max height to be w. So it's going to go from w down to that equation, but I need an x value. So that's going to be w over h times y. So what I will do is say that dm is equal to sigma times w minus w over h y times the width dy. So remember, this is the thickness from here to here is dy. This is w, and this has an x value of w over h times whatever your y value is. So we're going to integrate that, of course, from y equals 0 to y equals h. So I will carry out this integral, and I'll do them both simultaneously in this case. So I put in the integral, which is y times sigma w minus w over h y dy equals, pull out my constant sigma, integral of wy minus w over h y squared dy, again from 0 to h. And continuing on, I'll work the bottom in a second. Continuing on, I get the sigma on top. Now this will become 1/2 y squared, which evaluated at h becomes 1/2 h squared, and evaluated at 0 becomes 0. So I'll say sigma times w, sigma over 2 times w h squared, minus this one's going to become 1/3 y cubed. So that's going to be W over H with a 3 in the bottom. Actually, I should have put this 2 out there. I should have put the 2 in here. Okay, W over H with a 2 in the bottom, and WH squared with a 2 in the bottom, and then W over 3H here. And that, of course, would be H cubed. Again, the integral is going to be 1/3 Y cubed, but evaluated at H, that's 1/3 H cubed. Evaluated at 0, that's 0. And that's the top. Now the bottom's carried out the same way, except without this Y, so we get the integral sigma W minus W over H Y dy, which equals sigma, Now in this case, integrate W to just get Y. So it'll be WY, but evaluated at 0 and H just gives me WH. Then this one has a Y to the first power, so this is going to be minus W over 2H. And then evaluated at H gives me H squared. So under all of this junk, I have a sigma and a WH minus 1/2 WH squared over H. So you can see that this H is going to cancel out with one of those, leaving just a 1. So I have 1/2 WH subtracted from WH. And the same thing goes on here. This one breaks off, leaving a 2. So the top has a WH squared, but it's basically 1/2 minus 1/3 times that. So 1/2 becomes 3/6, 1/3 becomes 2/6, 3/6 minus 2/6 is 1/6. So I'm going to say this top is 1/6 WH squared. And this bottom, I have a sigma as well. And this is WH minus 1/2 WH, so that's 1/2 WH. So you can now see that the H cancels out completely with that. I've just left a 1 up there. The W cancels out, and the 2 is going to come on the top and become 2/6, which gives me 1/3 H is equal to the Y center of mass. So that's exactly as we expected. I told you the general rule is about 2/3 of the way to the bigger end. And from that, I predicted that would put the Y center of mass at 1/3 H, and lo and behold, I got 1/3 H. So that's how you can do a simple integral to determine the center of mass of a two-dimensional object. Hope that helps.